part is over. Now we have to do some managerial economics. This is what? Evening 6, correct? And the lecture has to be 16. So, managerial economics, lecture 16. And we're covering chapter 4 from the latest edition of, Thomas and Maurice, Basic Estimation Techniques. So, 4, we just call it estimation. Of course, when we say estimation, we do mean statistical estimation. Sometimes it's also known as econometric estimation. Basically, this is a quick review of elementary statistics. Unfortunately, there is no way in a couple of lectures to teach properly statistics. You're all expected to have had already a basic statistics course. You're already expected to know these things. You're expected to understand them. So, what I am expected to do is only to review those things. So, estimation is associated with some sort of functions. In business, you encounter a large number of functions for which you may have data and you may possibly need or want to have an estimate. This means you're going to be running the business. You're going to have a statistician who will do the statistics for you. So what you'll need is not actually manipulating the data and actually doing the statistics. It's more like knowing what it is, knowing what it means, knowing how to interpret the conclusions. So what type of functions you might have? Well, number one could be a cost function. You may want to be running the business. You will have some costs associated with some output. So you may have quantity output, cost quantity output, and you may simply want to say, hey, if I'm producing 250 units, what's going to be my cost? So you will have some cost function. It may occur in real world when you want to just estimate that cost function. Let's see other function. Another function will be a production function. Production function is a function which relates output to inputs. So we can sometimes say y, this is the output, is a function of input x1, x2, possibly up to n, a finite number of inputs. So you just want to see how each of these effectively affects the quantity of output, quantity of production. And another one, which is usual, is a demand function. You simply want to know if you have a particular price, what quantity of goods or services you would, under normal circumstances, expect to sell. So, this is where we need it. These are examples. Of course, in the business world, anytime you have some data, you may actually want to run and establish some relationship. So, first of all, you have a function. Function is typically a mathematical representation of a relationship. We call it quantitative relationship between one or more variables. So you have a function. Next one is parameters. So the function will be, the simplest in the world is a linear function. A plus bx. So let's throw in, while we're at it, y is called, dependent variable. I already explained very early, probably in the first lecture, what a variable is. It is a quantity which changes somehow over time. Dependent variable simply means that its value typically depends on some other variable. So dependent variable will be quantity that we sell, but it will depend on price, for example. Or output, 300 cars or whatever, will depend on some input. An example of an output will be consumption of a refrigerator. Well, of course, consumption of a refrigerator, given a constant temperature that you would like to maintain, maybe -3 degrees Celsius, is not, of course, constant. If you load up the fridge with a whole bunch of stuff, it's going to consume a lot more energy to keep all this stuff inside at -3. If the fridge is empty, of course, it will need a lot less electricity. So it could be consumption of electricity for a day, and the independent variable will be quantity of goods that we keep in the fridge. I'm just providing an example. So X we call independent. Independent variable. Independent simply means that in a sense we have a control over this variable. In a sense we can essentially change it if we choose. For example, the price, we can choose how to price our product, but if we choose how to price our product, then the quantity that we'll sell depends on it. For example, yield. Here is another reason we use Y in statistics. You know why? It's called yield. Yield is the same as output, production. And typically X, as an example, will be fertilizer. Fertilizer back in the old days. So, the quantity of fertilizer that we actually use in agriculture, we actually have a perfect control. We can choose 1 kilogram per acre, or 5 kilograms per acre, or 50 kilograms, or whatever the measure is. We can just choose whatever we want to choose. So, we choose certain quantity, we observe how much we produce, all right? And essentially what you do is possibly a agricultural plot like this. You put in a quantity of 1, of 2, of 3, of 4, of 5, 6, 7, 8, 9, right? So you know what quantity of fertilizer you put in there because you control it, because you just want to use that quantity. And then for each one of these, you measure the quantity of produce or yield. You measure the yield, all right? And then you just run a regression or just a plot. Oh, let's do now plot. Plot is simply or sometimes called a scatter. You just say, for 1, this is the output. For 2, this is the output. For 3, this is the output. For 4, this is the output. So, here you got X, let's call it fertilizer. Here you got yields, and you have certain yield. So, this will be a form of a plot. Usually the plot is done with straight lines. And sometimes this is called or known as scatter diagram. Scatter. And sometimes the scatter may have a smooth curve connecting the points, or as close as possible to the points. So, we said function, we said dependent variable, independent variable. A and B are parameters. A and B are parameters. Usually in statistics, a parameter is a constant which we attempt to estimate. let's see how I go about. In other words, what I'm doing right now is basically repeat or review quickly what these things mean. So to estimate, or estimation, is a statistical procedure which has certain acceptable mathematical or statistical properties, which is designed to give us, again, an estimate or an evaluation of what is the most likely value of the parameter. So, an estimate, for example, will be that, for example, in our case, if we have this relationship here, 0 fertilizer, 1 yield. 1 fertilizer, 1. This is 1.5. 2 units of fertilizer, 2. 3 units of fertilizer is going to be 2.5, and so forth. So, an estimate of B here is, what is it? 0.5. 0.5. So, if we have a computation, so an estimate is based on a computation or a formula which gives us an attempt to show us the true value. True value. So, now our next concept is true value. So, true value is the actual, real value, which is the correct, proper value. In other words, if you have a functional relationship, that functional relationship has some real, actual, true value. Okay? And the idea is that when we provide an estimate, that estimate will give us a number which is very close to the true value, to the true number. The idea, of course, is that you're plotting. This is agriculture. Maybe you had a little bit more sun, and the sun affected the crop. Maybe you had a little bit more of a rain, so the rain affected the crop. So, for each of these, you have some other factors. Maybe wind. Maybe animals went through and damaged a little bit of the crop. In other words, when you are observing these are just observations. These observations are based on a true relationship and on some error term, epsilon. So if we have T, this becomes T, and this becomes T. The T could be the wind, could be the sun, could be the animals, could be a whole number of different elements. So, these error terms will actually affect our estimation, and if the true estimate is 0.5, the true value is 0.5, our estimate might be 0.048. So, 0.48 instead of 0.50. So, the idea is that the estimate, under normal circumstances, will tend towards the true value. But of course, if you repeat the experiment next year, you're going to get other yields. And the first year you're going to get, for example, 0.48. Second year you're going to get 0.49. The third year you're going to get 0.511. Then you're going to get 0.53. Alright? So, each year that you run the experiment, each year you're going to get a different estimate. The idea is that when you take the estimate over a large number of experiments, the average of the estimates will be close to the true value, will approach the true value. And we call this property unbiasedness. So, the estimator is unbiased. if given sufficiently many repetitions of the experiment, the average will tend towards the true value. Alright? So this is what means unbiased estimator. Oh, so now we get to the estimator. Estimator. Estimator is the formula which we use to get the estimate. So the estimator is a formula which we properly call a function, and the estimate itself is a value or numerical value. In other words, the estimate is just a number, while the estimator is a function. Alright? So in this particular case, we say that we have an unbiased estimator, and the estimate is unbiased. Alright? Clear so far? Let's see what other things. Parameter. Alright, so when we are trying to fit some sort of a curve, usually we use, or the model type is called regression. Regression is associated with fitting data to a particular type of a curve, predetermined curve. When we say now linear regression, this means that the curve is a straight line. Okay? A different way of saying the curve is a straight line is that the independent variable is dependent on dependent variable by a constant. Alright? You may have 2, 3, or 5 independent variables, but you don't have the independent variable as squared or cube or anything else. You have the independent variable only to the power of 1. Okay? So we call this linear relationship. Okay? Linear relationship. And linear regression is the method by which we attempt to establish which is the best relationship or the best fit. So I'm going to be explaining in a few minutes what best means. Okay, let's see what's next. So, as I explained, our goal is mostly to interpret and use. So, in this course, or at least for now, all we're trying to do is how to interpret regressions and how to interpret, in general, estimations and how to use them. We're not trying for you to actually do this. This is done in statistics course or in a more specialized course called econometrics. Okay? And the idea that we provide is usually, this is usually based on intuition. In other words, we're trying to appeal only to the senses. We do not try to provide rigorous mathematical derivations. Alright? Well, let's see what we have in 4.1. So, 4.1, regression analysis. I covered it. Number 2, dependent variable. I covered it. Number 3, independent variable is also known as, which is the same as explanatory. Explanatory variable. So this is a variable which actually explains the independent variable. So explanatory variable will be the fertilizer because it explains the yield. Alright? Next, I already said what is linear regression. The next to explain is the word simple. So most of the times, not always, we use simple linear regression. Simple linear, simple has, yes, very simple meaning. The regression has two variables, but it's nicer to say that we have only one explanatory variable. So it simply means one explanatory variable. In our case is fertilizer. Of course, we can have, instead of simple, multiple. Multiple. Simple regression will have one. Multiple regression will have two or more explanatory variables. In our examples of the agricultural plot, the second variable will be rain. Okay, rain. So, fertilizer and rain. Of course, you will be using this over a number, 3, 5, 7 years, and you will have also variation in the rain too. Of course, you may use a third variable, sun. Sunny days, number of days with a sun, alright? That could be a third variable. So, what you're trying to use is the most significant variables. Significant has two very different meanings. One is economically significant, something which actually has economic meaning, meaning affects profits and profitability significantly. And the other one is statistical significance, which I'll be covering probably in the next lecture. Okay, so the parameter A has a very special name. It is called intercept for short, and is called intercept parameter. Intercept parameter. It is called intercept because whenever you have a straight line or any curve, any mathematical curve, wherever the curve crosses the ordinate or the vertical, we call the point of intersection, which is this one here, between a function or the curve of a function. We also call this the graph of a function, with the vertical axis, alright, we call this, or the y-axis, we call it the intercept. So, A we sometimes call intercept, but it's technically called the intercept parameter. And of course, the next one is B, which is the slope, or respectively, the slope parameter. The slope is simply what it is. It shows you the angle of the curve relative to the x-axis. So one way to do it is to draw a horizontal line parallel to the horizontal axis and measure the angle, and this will give you the tangency of the angle, well, just a mathematical representation of slope which you should have studied in high school usually, right? Alright, so let's see what's next. Linear intercept slope, linearly related. Okay, what if it is curvilinear? Curvilinear simply would mean that the relationship is not a straight line, but is a curve. An example will be, let's draw a picture, a quadratic curve. A quadratic curve will be like this. A quadratic curve like this. In this particular case, it's of the type ax squared plus bx plus c. The curve could be logarithmic, okay? It could be exponential. Simply means that the function is non non-linear. Non-linear. And when it is non-linear, it is drawn as a curve, and we call it curvilinear or simply non-linear. Now, we deal mostly with linear regression, and whenever we have non-linear, we attempt to provide or to make a transformation, mathematical transformation, by using logarithms, powers, or some other mathematical transformation that will linearize. Linearization is the process of getting a nonlinear function, and by using a transformation of the independent variable to actually linearize it, make it linear. You should have ideally, how many of you have studied or at least heard nonlinear and linearization? Most. Okay. Let's see what's next. Okay, so we have true, let's do this. We have a true relation. True relation is the true, genuine, actual relationship which is operating, which is valid. And out of a true relation, you will get the true values of the parameters. In other words, a true relation is only one. It is just one function. And the true value, each parameter will have its own true value. So the true value of parameter A, we call it the intercept, and the true value of the slope. So each parameter will have its own true value. And the whole, the set of all true values with the functional form we simply call the true relation. All right? Let's see what's next. Okay, linear regression. Out of linear regression, you get the next one, which is, let me see, I'm trying to see how to do this. Regression line. If we're going to be doing linear regression, we will be always getting a line. Regression line. So, regression line is actually the line that we get as a result of applying linear regression analysis. Linear regression analysis. So, we have our yields. Alright, I just drew points. These are our yields. The regression line is simply a line, or the line that we get, and we just draw it. Which fits the data best. I'm getting to the best part soon. Alright? So, we simply call this the regression line. Alright? Fair common sense? Let's see what's next. Next. Alright, true value, expected level. Okay. Now, this little thing here, which we sometimes designate with the Greek letter epsilon, they should have used Arabic letters, right? This would be a nightmare for Westerners. So, we call this error term. Error term. Now, you have error term sometimes with epsilon, sometimes with E. Actually, I should have had it as E. Let's try to do this and explain this very simple thing while I'm at it. Well, I'm trying to cover a full course in statistics literally in 2 hours, and I'm trying to do the impossible. Of course I can't. So, but I will A plus, let's try this, let me do this. Y equals A plus BX plus E. So, A is the slope parameter. Then, the estimate of the slope parameter becomes alpha. All right? Is this familiar from statistics?
Was it the slope or the intercept?
This is the intercept minus that. The intercept. The estimate of the slope, which is b, becomes beta, sometimes pronounced as beta, again depending on accent, American, British, and English, etc. So it becomes beta x. And then you have E epsilon, which is the estimate of the error. This is the true relationship. And we use Latin letters. And for this one, we use, which is the true, this is the estimate. We use Greek letters. We use these by convention. Convention means that statisticians around the world got themselves into a congress and decided from now on we'll use Latin letters for true and Greeks for estimates. All right? It's just a convention. They've agreed to do so because when you read things, it's nice to know if you're talking about the true parameter or the estimate of the true parameter. And this is the general agreement. So, this piece here we call the error term. What the error term does is capture random effects which are due to some other factors, some other variables which are not part of the equation. In this particular case, we used fertilizer, so the error term will capture the effect of the rain, the effect of sun, of wind, maybe of other animals, maybe of other geographical or some other factors. These will be all incorporated into the error term. The idea is that this is very significant. The idea is that X, the fertilizer, is by far the most significant and will capture most of the variation in the yield, but the others will have relatively small effect on the yield. All right? That's the idea. That's the concept behind it. So, no matter whether it's large or small, we simply call it the error term. Okay? Let's see what's next. Next is actually 4.2. Let's see if you girls have a question. I'm here. No questions? Okay. I mean, if you have questions, just ask me. That's what I do here. All right. So the next section is 4.2, which is fitting a regression line. So, the first thing that we have is that of estimates of the parameters. So, whenever we have parameters A and B, we try to get or find an estimate. An estimate is what we think the relationship is based on the data that we have, which we hope approximates best the true value. Simply because we can't always possibly know the true value, we're trying to get the best we can get. Okay, so they are telling us that we have a number of types of data. So the first major type of data we call time series. Time series is actually one series. Okay, it's actually one series. It's actually one variable for which we have observations over time. Unemployment will be time series. In January, 2.3 million. In February, 2.4 million. In March, 2.5, etc., etc. Interest rates will be also a time series. 3.7, 3.8. stock market prices. For each day, the stock market closes at a particular value. That's yet another time series. So, usually, or not usually, most of the times we deal with some sort of time series. This is the value of one particular variable over time. Now we get to cross-section. Cross-section or cross-section data, sometimes we call cross-section data set, is data which is usually produced at one point in time, usually for the same variable, for the same type of variable. This is the excellent example, the classical example of a cross-section. Cross-section means you kind of like use it in cross, like just like this. So you use, here is one, a second, the third. So right now what I generated 9 different cross-section observations. Okay. A different type of a cross-section observation will be unemployment. But unemployment was a time series? Yeah. Well, unemployment for each state in the United States. You have 50-some states. So California one unemployment rate, Florida second, New York, Ohio, etc., etc.
At the same time?
At the same time, yes, yes. Today, you have for each state its own cross-section data, meaning unemployment data, okay? An example of cross-section data will be, for those of you working, your salary. 25,000, 23,000, 17,000, 19,000. This is for the month of November. It is for the same time of the salary of 25 different people. They will have different salaries, all right? So this is cross-section. And then you can have that mixture of the two, which we sometimes actually have in the real world, which we call panel data. Panel data is a time series for a cross-section. Oh, what does it mean? It means that you have an observation. Unemployment for Ohio in January. Unemployment for Ohio in February. Unemployment for Ohio in March. April, May. Unemployment Florida January. Unemployment Florida February. Unemployment Florida March. And then you have for all 50 states or for whatever states, you have the unemployment for each month. So we have 50 states, 12 months will produce 600 observations. Well, this type of data, which has both the nature of time series or provides a time series for cross-section data, will be called panel data. Well, how do we do this over here on the plot? Well, on the plot we'll do a second plot. The first plot is the year of 1999, right? You've heard the expression party like 1999?
1970.
No, 1999, party like 1999 means that this was the dot-com telecom bubble when everyone was investing, everyone was making money. This was the wildest party in the history of the world, right? So, this is 1999, and then this is 2000. Here, the rain and the wind was the same for the plot, all right? Here, of course, next year the wind was different, the rain was different, the sun was different. And then, if you really want to go on with the panel data, you go to 2001. Alright? So, these are the 3 basic types of data sets. Time series and cross-sections are the 2 basic ones. And panel data is a combination of the 2. What's next? Next. Population regression line. Population regression line is simply the regression line which fits best the whole population. So now I have to explain what population means. Well, what's population? Well, what's the population of Saudi Arabia? 20 million. All right. Well, what's the average age of Saudi population?
Teenager, I think.
Huh? 28. Well, we just assume I can't ask. What's the average population of you here in class? Let's say 23. I'm just picking a number, right?
Don't ask about the age.
Right. I'm not asking about age. I already assumed it's 23, right? Yeah, it's a very good age, I'm sure. So, well, you here in class represent a sample. So, the one concept is that of a population, the other one is of a sample. Population and sample relate to members. Population refers to all members of the data set, the complete data set, okay? And sample refers only to a part or a portion, sometimes we just call it a fraction of the full population. Now, why do we often use a sample in statistics rather than population? All right?
It's hard. It's time-consuming.
It is hard, but hard doesn't make it impossible.
Costly.
Costly. It is costly. So, it is time-consuming, and so it is consuming resources. The two basic ones are time and money. In other words, time-consuming. It's just costly. It just takes way too much time, number one. Number two, a lot of times you just cannot possibly use the whole population. Let's provide an example. An example with some medical drug that is supposed to cure whatever. Let's call it fatness, all right? And if we want to test it, do we want to test it on the whole population? The answer is hell no. No way. I mean, you test it on 20 million people, it's got a side effect, and it damages your liver. You end up with 20 million people with a damaged liver. It's going to be a disaster for that particular nation. What you want to do is test it on a small sample of the population. Maybe 20, maybe 500, I don't know. It depends on what's medically right or what's economically correct. And maybe you test it also on some people initially that have maybe, so obese that the damages might not be that terrible after all. Or they may have some other difficulties anyway, and at least you want to see what happens on this one, all right? So sometimes you just cannot possibly, from common sense, cannot use the population. Other times, you just can't, even if you want. I mean, sometimes you try to test something on 300 million Americans. Well, how can you even test something with 1.5 billion Chinese, all right? And then there is that other problem. Some of these, of the whole population, might be untestable. You try to test something that requires their reading, many of them can't read, all right? So the answer is, what you want to do is simply take a sample. And if the sample will represent or will have similar properties to the population, we call that the sample is representative. Representative sample means that the sample is very similar in its characteristic to the full population. Are you representative? No way! No way! You're not representative of anything. First, you're not representative of age. Alright? Is that more or less true? Right? I mean, actually, your age is in a very narrow range. Between 23 and, I don't know, 26, right? Number one. Number two, you're not representative of education. You already have bachelor's degrees, right? How many females have in Saudi Arabia percentage-wise a bachelor's degree? 20? 30?
No, 70.
70%. Oh, then you're well represented. And then there's the last thing. You're all female here. You're not representing the Saudi population. You got a lot of males. In other words, you may be representative of female college graduates, but you're not representative of Saudi population. Alright? You are probably very well. Then again, you're probably not even representative female college graduates because a tiny fraction of them will actually go to grad school. And you have all chosen to go to grad school. You're probably some of the best, or the smartest, or the small percentage that are actually working, or whatever your reason is, you have a reason, and given that only 1% of all with a graduate degree will go to a master's, with a bachelor's degree will go to a master's, you're certainly not representative of all of those,
So
all right?
representative of ladies studying masters and studying.
Yes, you're much more representatives of females studying masters or possibly recently graduated with a master's degree. All right? Now, because you're not very well representative only those with, let's say, with only those with bachelor's degree, because you chose yourself, your sample is not representative. Let's introduce a new term which is not in the textbook. It is called self-selection bias. Self-selection bias. Self-selection bias. This simply means that you all selected by yourself to pursue an MBA, and your sample will incorporate some bias. The bias will be maybe you're business oriented, they would rather have, or the majority actually do have, a degree in what? History, Egyptology, Islamic studies, right? These are the three most popular majors. Some other liberal arts, culture, whatnot. And you're all doing business. So, you're already in the minority. But the problem is not whether you're in the minority or the majority. The problem is that you're too different from the overall sample of college graduates. And the difference shows up because you chose to pursue MBA. Alright? Time out! Okay. Whew. Let's take